another Lightblade Learning Lab. Now today I'm going to attempt the impossible. Now you may laugh at this, but I'm going to attempt to tell you virtually everything that I know about graphics and how we deal with graphics on this machine. Now I can hear you laughing because you think that I probably know about that much about graphics, because I've purposely steered away from the subject up to now. We've talked a little bit about it, and I think, as you can see, I can make a moderate attempt at getting a picture down onto a piece of material, and I can show you quite a few more examples. But that does not mean to say that I actually know what I'm doing. That was a bit like shooting bullets in the dark. Yeah, I fiddled around with a few parameters and I got some reasonable results, which is promising for you guys because it means you don't need to know very much to get some sort of result. But the problem there was I was having to fiddle around to get the parameters. So I decided I would embark upon trying to understand what graphics was all about. Now I have documented all my mistakes, all my learning processes that I went through to get the information that I'm going to pass on to you today. If you want to go into great detail, then you should you may want to waste a bit of time and look here at my other video channel. But to save you the tedium of doing that, I'm going to attempt the impossible today and put something like about 6 hours worth of video into maybe 3/4 of an hour. So sit back, be patient, and we'll see what we can do to explain this subject to you in fairly simple terms, in a way that you will fully understand what this machine can and cannot do in the way of graphics. Okay, now I'm going to scan two images on this page, and I'm going to give you a clue. They're both going to be scanned at the same speed, and they're both going to be scanned at the same power. Power is about 4 watts coming out of the tube, minus the efficiency of all the mirrors in the lens. So there's probably only about 2.5 to 3 watts arriving at the paper surface here. So it's a piece of white card with 2.5 watts going down onto the surface. Now what I want you to do is to use your powers of observation to see if you can determine the difference between scan 1 and scan 2. Well, what do you think? Do they look any different? I think you'll say the answer is no. But believe me, they are very different in the way in which the machine has produced them. And that's what the whole of this session is going to be about. The difference between those two pieces of text that actually look the same but have got completely different characteristics. Let's go and have a look at what the program is that I used to send those two pieces of information down to the laser machine. Okay, well here we are in RDWorks, and you can see the two words text on the screen. Now if we look up here at the top right hand corner, you'll see that one of them is called BMP and the other is called nothing. And that's because that second piece of text has been produced like this, 50 millimeters tall. And I will change the font so that it doesn't get confused with anything else, and we'll turn it into a script font of some sort. There we go, like that. Not very pretty, but it demonstrates the point that I'm making. When you create a piece of text in RDWorks, it comes in as an outline font. Now that outline is
basically a vector graphic outline. And let's just make it blue for a minute to demonstrate. Put it onto a blue layer. Now that blue layer can either be set as a scan layer, which it is here, or I can set it as a cut layer, like that. It doesn't look any different. The only difference is that the machine will treat it differently. This cut layer is exactly what it says. If you cut that word text, it will fall out and leave a hole in your material. If we convert it to a scan layer, as I said, it looks no different at all, but this time something different will happen. Now you can see the other two pieces down here, and there's the big one at the top. Let's just do a simulation and you'll see what happens. Now it's going to scan from the bottom, and when it gets to this one, it's going to scan it, lines across the page. So the hollow text there basically means it's uncommitted. You can have it cut or you can have it scanned. Now what about the black text underneath? Well, it's come in as a bitmap. You can't change that because that's all to do with how you produce the text outside this program. And this piece of text has been produced in something like Photoshop or some other art package where you might produce your drawings and you import them into here as a bitmap or as a JPEG or a PNG or some other form of basically a bitmap type file. In reality, when I engraved these, they both look the same, but here as a text file, as you can see, it's pretty blocky around the edge. Now I might be talking down to a lot of you guys, but there'll probably be people out there that do not understand what a bitmap is in relation to a vector file, which is the text drawn above it.
Okay, well here we are close in on our two pieces of test text, and I don't think you can really see any ragginess around the edge of the bottom set of text. It's still pretty clean. That is solid black text. Now, although this is a very largely magnified part of a picture, I think you'll be able to see that there is an eye in that picture with a pupil and an iris around the outside. It is not a solid colour. It's made up of lots of little pieces. Now, those little pieces are called pixels. And every one of those pixels on that screen there is mapped with an X and Y coordinate so that the computer knows whether one pixel on the screen has got to be turned black or white. So there's a huge amount of data that the computer has to process to store a picture like this. Now let's just go and take a look what I mean by pixels and this strange word called resolution. The resolution of a picture is described in terms of PPI, and I'm going to draw this one at 300 PPI, pixels per inch. Now that's the standard industry format for resolution, and this particular picture is 300 PPI horizontally, and it's also 300 PPI vertically. Makes sense because they're squares. Now when it comes to working in RDWorks, most of you guys will have your machines set to work in millimeters. If you're one of the very few people in the world, which probably includes America, that uses inches still, you will otherwise have to use millimeters. What we need to do is to establish what the size of one of these pixels is. Okay, now I've scribbled on this piece of paper here a very simple calculation that you can carry out that will enable you to convert from pixels per inch down to a size of a pixel. So the first stage is to take 300 pixels per inch and divide it by 25.4. Now there are 25.4 millimeters in an inch. So what we're really trying to do is to calculate the number of pixels in a millimeter. And the answer to that is 11.81 millimeters in a pixel. So that's pp millimetre, pixels per millimetre. Now if we want to find out the size of a pixel, if we know how many pixels there are in a millimetre, if we divide the millimetre by 11.81 pixels, it tells us that we've got 0.0847 millimetres is the size of that pixel there. So that pixel there is 0.0847 millimetres square. At some stage when you're setting up your scan parameters, you will be asked the question, what is the increment? And that will be asked for in millimetres. That's the answer to the question, 0.0847, because you want to step down 1 pixel at a time in the Y direction. Right, now the machine cannot produce square shapes. It doesn't work in pixels per inch. Although pixels per inch is the thing that drives the machine, what actually comes out of the nozzle are round dots. You've seen it for yourself. When you do a pulse burn down onto a piece of paper, if you set the focus right, you get a very, very fine dot. The machine works in dots per inch, and the resolution of the picture that you're trying to produce is in pixels per inch. You would say, yeah, but the machine is going to automatically convert squares into dots as it runs across the page. Well, you are absolutely right. Every one of these squares tells the machine to do something. If we look at these pictures, they do match up. It decides whether it's going to put down a black dot, nothing, a black dot, nothing, black dot, black dot, black dot. Now, you might assume that that's pretty logical. Most people don't understand that the machine can and does work in dots when it's using a bitmap as a driver. And I'm using that word a little bit carefully, as a driver, because there is another thing that can be used as a driver. Now I'm just going to draw 2 things that look approximately like circles. And this circle here is made up with pixels. And this circle here is not made up with anything at all. This is a vector, because it has only got a ring around the outside. And this one is a BMP. It's a circle made up of squares. How the machine sees a bitmap, every time it sees one of these pixels, it sends out a pulse. Or not. Pulse or not. Now, when we've got a black picture like this, which is filled in, it's filled in with a series of black dots. And it's the collection of black dots that makes the image look solid. Now that's not the same when we've got a vector drawing. The laser doesn't go and put dots on here. What it does, it decides it's going to scan backwards and forwards across this image like this. And as it goes across, it'll draw a line with the laser. So we get a line that goes across there like that. And then it comes back and we get another line. And then we get another line. We do not get dots. We actually get lines that go backwards and forwards across the image like this. Now I've purposely drawn these as lines with big gaps between them. But what you do, this is where you set your increment. And you can set your increment so that the lines join up. And that then becomes a solid black shape as well. But as you can see, the mechanism by which the bitmap is produced and the vector shape is produced are completely different principles. And that is a very, very important thing that people do not know or understand. It took me a long time to find out this difference. This is a piece of perspex looking from the back of the perspex at an angle, so that what we can see is a black rectangle that I had produced. And the black rectangle is obviously made up of every single dot in the bitmap, and you can see those dots on here. Now, when you look at it from the front, it looks like a solid black shape, but when you look at it from the back, you can clearly see that that solid black shape has been made up by dots that join together. Now, that is a very, very important principle that you need to understand about producing graphics. Well, we're not really going to talk much more about this one, because this one is very simple. It's just lines and spacing, increments. This is the one that's very, very interesting to explore, because if you want to put a photograph down onto a sheet of any material, you will have to use a bitmap image to start with, because that's what photographs are. The cleanest way of producing a picture like this is probably to do it in CorelDRAW, and it may well then give you a DXF output so that you can produce a vector file which you can then engrave across. And this is a nice simple way of producing block graphics, logos, text. All the complications and difficulties come with doing something which is a bitmap. And this is what I spent a huge amount of trying to understand. This took me quite a long time to find out, and I was quite staggered to find that every dot in the bitmap can produce a signal for the laser beam to pulse. This picture depends upon the size of the dot itself and the resolution of the picture. Now, there are many different focal lengths of lenses that you can use in these machines. The most common ones are 1.5 inch, 2 inch, 2.5 inch, and 4 inch. Now, every one of those lenses has something called a theoretical spot size. Now, that is the smallest size dot that you can produce with that lens. And a 2 inch lens has got one which is a little bit bigger, and a 2.5 inch lens has got one that's even bigger still, and a 4 inch lens has got one that's even bigger. This is about 0.075 millimeters, which in old money is 0.003, 3/1000 of an inch. And this one is 0.100, which in old money is 0.004 thousandths of an inch. And so they go on, and they get bigger and bigger as the lens gets bigger. This is probably the lens that most of you will have. The Lightblade machine is fitted with one of these. Now, in terms of size, you can see that it is very, very little difference. Now, I don't know whether you can see that, but that's 2 of my grey hairs there. That hasn't helped my bald patch, has it? The size of that hair is roughly 0.003, 3/1000 of an inch, or 0.075 millimeters. So that just gives you an idea of just how small the spot size can be. And this, at 0.004, you would not be able to see the difference between a 3 thou and a 4 thou hair. So don't get too concerned if you've got a 2 inch lens in your machine, because it is not going to be a disaster when it comes to doing bitmap graphics. It makes a big difference to the area, the energy density. You'd concentrate 60 watts into that size and then put 60 watts into that size. The energy density there is almost, well, it is twice as high as it is in this one. So in terms of cutting power, this change makes a big difference. But in terms of engraving power, it makes no difference at all. Okay, now I've just drawn up a few little features on here. Having decided that this was roughly the thickness of a human hair and we don't have to worry about it in terms of resolution, ability to produce a dot, what we have got to worry about now is power, because we can produce these dots at very, very low powers. But as soon as we start putting power into the dot starts doing this. It gets bigger and bigger and bigger. Now, that's not what we want. If we want fine resolution pictures, we need the smallest dots that we can possibly get. Ultimately, what we're trying to achieve is a picture made up of dots, different density areas, just as you see them in a newspaper photograph. If you look at it very closely, you'll see that it is exactly that, a series of dots. And in fact, we've already seen that today. Here's how the eye can be fooled. Much further away, and you wouldn't even see these dots. You just see what looks like a photograph, a grayscale photograph. And that's one of the magic tricks that happens between the eye and the brain. It has this ability to heal over all these little imperfections and produce a lovely picture for you to look at. So, we need the smallest dots we can get, and to achieve that we really are looking for a small focal length lens and very low power. Now, how does speed affect it? Well, up to about 100 millimeters a second, the dots really don't change too much away from circular. But if you start going 150, 200, 300 and 400 millimeters a second, then here's what happens. Your dot turns into a sausage, a short sausage. And then the faster you go, the longer the dot becomes. But this black set of pictures that I've drawn here is not quite right, because there's another phenomenon that occurs in parallel with that. Now, if you use a larger power to start with, you get a bigger dot. And if you start then increasing the speed of that larger power, here's what happens. You get a sausage, but the sausage is smaller than the dot. And as you increase the speed, the sausage gets narrower and narrower. And so you get back much more towards the original dot size here. So consequently, if we start looking at how these lines, sausages, now sit on this picture here, bear in mind we get a pulse for every pixel. These are dots, but we're still going to get a pulse here, a pulse here, and a pulse here. So that means we're going to get a dot there, a dot there, and a dot there. The dots are going to start joining up, and they're no longer going to be seen as dots like that. What we see is that. Now that looks much more like the vector scan, but it isn't, because it's still driven by dots. And those dots that drive this are producing some really weird effects. Now, it would be very nice if we could produce dots and our picture looked like this. But when we actually burn dots into a piece of paper, what we get is something like this. Now, we've got brown dots, slightly brown dots, and lots of other different grades of brown dots in the background. But hey, if I was producing a proper dot graphic like this, all these dots would look the same. It would look like the measles. They would all be nice and black and at the same quality. Now, the question is, why are they all different shades of brown, different power? The shade of brown tells us the amount of power that's gone into the dot, how much the paper has scorched. When we're doing dot graphics like this, we have the power set to, say, 11% and 11%, max and min. There should be no variation in the grade of the dots. They should all be exactly the same, little black dots. But they're not. And the question is, why not? Now, just coming back to this, this was done 50 millimeters a second, very slowly, but it's done with 30% power, 35 or 40 watts of power coming out of the tube. And this is a resolution of 100 pixels per inch. That's what this picture was done at. If we start going faster than that, we lose our individual dots, and we get lines where the sausages are all joined together. So our 100 pixels per inch at 50 millimeters a second, which enabled us to produce this lovely pattern here, single dots, is what I would class almost as the holy grail that we're looking for. We're looking for the ability to produce good, clean, single dots to try and get my measles effect that I call it. You know, we want nice uniform coloured dots all over the picture so that we can produce the same sort of picture that we produce with an inkjet printer. Just two colours, black and nothing. So the background is left bare and every one of these little burns is exactly the same colour. Now that's what we're aiming for. And this looks as though it's going to give us the parameters for achieving that. So here we've got 100 pixels per inch. Divide that by 25.4 means we've got 3.94 pixels per millimetre. And so here we've got 50 millimetres per second as the speed that we're running at. So if we want to work out how long it takes for 1 millimetre's worth of travel, we take 1 millimetre and we divide it by 50. And that basically gives us an answer of 0.02 seconds per millimetre, 20 milliseconds. If we now take the 20 milliseconds, in other words, that's how much time it takes to travel a millimetre, but we know that in a millimetre we've got 3.94 pixels. So if we take the time it takes to travel 1 millimetre and divide it by the number of pixels in that millimetre, we get approximately, let's just call that 4, for example, 4 pixels per millimetre. It's a nice simple calculation and we get approximately 5 milliseconds per pixel. So that's the amount of time that it takes to actually put one of these pulses down. Now, if we start messing around with anything faster than 5 milliseconds per pixel, then we shall start producing something which is getting closer and closer to this. So at the end of the day, the crucial thing is how much time we're spending putting a pixel down. And that depends on the resolution of the picture and the speed at which we do it. If we want to remain at 5 milliseconds per pixel, which really is what I class as almost a golden number, then we can either change the resolution of the picture from, say, 100 pixels per inch to 150 pixels per inch. In other words, we can increase the resolution and make it a finer quality picture. But to do so, what we've got to do is we've got to reduce the speed from 50 millimeters a second to 33 millimeters a second to allow the same amount of milliseconds per pixel. Consequently, we could also do it the other way around. We could make the picture much, much coarser, down to 50 pixels per inch. And then we could push the speed up to 100 millimeters a second, which would still give us 5 milliseconds per pixel. What I'm going to do is to show you this information in a slightly different way. So just remember we've got 5 milliseconds that we calculated for 50 millimeters a second, 100 ppi. So for that resolution, that's how much time we have for every pixel. Now what you see here is a relative set of resolutions. This is 100 pixels per inch, 150, 300 and 600 ppi. These are all drawn to scale. And what that means is the pixel size for 100 ppi, it's 0.254 millimeters. It then drops to 0.169, 0.084 and 0.04. 0.04 is just over the thickness of a human hair for every pixel. So just to keep that in perspective. Now, what that means is, as we've already seen, at 100 ppi, we can calculate, if we run this at 50 millimeters a second, and every one of these is run at 50 millimeters a second, we've already calculated on the previous sheet that it takes 5.08 milliseconds for a traverse across 1 pixel. Now, if we start halving or we go to 150 pixels per inch, that changes to 3.39 milliseconds as opposed to 5. And when we get to 300 pixels per inch, it's down at 1.69 milliseconds. And at 600 millimeters a second, it's down at 0.85 milliseconds. So we're getting incredibly short periods of time allowed for every pixel. Now what I'm trying to illustrate with this drawing is that the time allowed for every pixel is getting less and less and less as you increase the resolution. You might think you're doing a great job of increasing the definition of your picture, but what you're actually doing is allowing less time for the laser beam to burn in one spot, and therefore the colour of the spot will be less dense. Now that's true if you're using something like white card or an organic material like wood, leather, but of course that won't apply if you're using glass or slate or granite or something like that. We get a completely different effect. So let's stay with white paper, card or wood, where we get grades of brown depending on the power that we put into the dot. Now things are starting to get quite complicated, because although I've broken this whole problem down into little individual elements like this, they don't actually and can't actually exist like this in reality. A typical dot size for a 2-inch lens will be probably somewhere in the region of about 0.2 in practice. I know theoretically it should be 0.1 of a millimetre, but in practice when you start burning it you'll find it very difficult to get much less than 0.2 of a millimetre. So therefore when we start looking at a 0.2 millimetre pixel in here, that's what it looks like. Now at 50 millimetres a second, we're talking about using small amounts of power here, by the way, say 11%, very, very small amounts of power. And we get that size pixel, the best one that we can get. Now, if we carry on using 11% power and we move the resolution up to 150 ppi and we try and put the same pixel on there, that's what we're going to get. We're going to get a dot that overlaps with the next dot. And then when we try and do it at 300, we're going to finish up with the same dot and the same dot. But look what happens, it's covering more and more pixels. But remember, the machine is driven by the pixels. So consequently, what will happen is we shall get the first circle here to match the first pixel. And then the second pixel will drive another dot. And so we shall get another dot here. And then the third pixel will drive yet another dot. And look, I think you can see very clearly that we're getting dots overlapping on dots, overlapping on dots. So we're getting multiple burns. And the finer the resolution, the more burns we get in X. And of course, then we start stepping down in Y. So we're going to get multiple burns in X and in Y. We've got a few parameters that are getting mixed up here. We've got the dot size, which is remaining constant, even though the resolution is getting smaller and smaller and finer. So we're getting more and more overlaps, which technically means we probably could be getting more darker burn. But of course, counteracting the darker burn, we've got the opposite effect, and that is the fact we're getting less time for each one of these burns. So although we technically might have a darker burn because we're getting multiple burns, we're getting substantially less power because there's less time for the dot in one spot. Now, you can't second guess what the result of this is going to be. I'm just telling you what the problem is that you're facing. What we should do is find out how these things affect a picture in the next session when we start building pictures at different resolutions. But for the time being, what I'm trying to do is to explain to you the problems that we're going to face so that you can understand all the details associated with producing graphics. Now you can see that we've got less and less time here for our burn to take place. But what we haven't considered is whether the machine itself can operate this fast for putting a pixel down. And so I've done some work on both of my machines to see how good they are at responding to a demand for a pulse from each one of these pixels. Now we know that this one works because there's the picture. And so I've done some more work at 50 millimeters a second and 100 ppi with a different pattern, and I'll show you the results of that pattern. What you're seeing here is the penetration of the beam into a piece of perspex. Now this is looking at it from the back so that we can see the penetration into the perspex itself. Look, you can see these little peaks. So we're looking at this from the back side at about 45 degrees so that we can see the penetration. And what I've done, I've generated a pattern here which is basically 1 pixel, and this was all done at 100 pixels per inch, the resolution. So we've got 1 pixel, and then we've got a 4 pixel gap, 2 pixels, 4 pixel gap, 3 pixels and a 4 pixel gap, and we did that all the way up to 10 pixels. And so that's 1, 2, 3, 4 as it says on here. I have the 10th one is missing. What we find is that the rise time, the time that it took for the beam to form, that green line is virtually nothing. This was 9 pixels wide, and what's happened is we've got some very strange effect taking place here, and then once the beam switches off at about here, we've got this pink line which shows the decay of the beam, the time the power actually takes to disappear. And so you can see that that pattern is exactly the same on every one of these patterns here, whether or not we've got 1 or 9 pixel groups. So the rise and fall times are very consistent. Now the reason I'm showing you this is because just one of these pixels that I'm showing you on here is this. So these are the single pixels that we can see here. These pixels here in the background are single pixels, and they're the same pixels as you see here. Now, what I'm now going to do is to just try and explain what we're seeing here with these funny shapes. Now, on this pattern here, I've just drawn a nominal pixel pattern. There's a black pixel, nothing, black pixel, nothing, black, 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 nothing, black, black, nothing, black, nothing, black. Okay, now what we've got here is a little picture of the beam switching on and off, and that's what that black pattern is in the background there. That's the maximum power that we could expect the beam to achieve, and this is theoretically what we're expecting to see. We get a pulse, here it is, creating a black dot, and then we get no pulse, so we get nothing. Then we get another black pulse, and so it runs. And here, where we've got a group of 3, we've got pulse, pulse, pulse. We've already proved that, and I keep coming back to this picture so you don't forget it. We're driving this laser with individual pixel pulses, and I'll just remind you of this picture here. Green is the beam on, and pink is the beam switching off, and you can see how much drag or how much lag, delay time there is in switching the beam off. The beam switches on, and it never makes it to this maximum that we were trying to go for, the maximum power. Why not? Well, because it has to switch off, and it takes a long time to switch off, so therefore it starts switching off early, and it never makes it to this maximum position. And we can see that clearly on here. Look, there is a 1 pixel. There's 2 pixels, and 2 pixels joined together are higher than 1 pixel. 3 pixels joined together are higher than 2 pixels. 4 are higher than 3, but then that's where we start to stabilize out. Once we get to 4 pixels, we've achieved a uniform height. So basically it takes almost 4 pixels to reach the ideal depth, the maximum depth. Now I haven't quite shown that on this diagram here, but what we've got a rise time and a fall. Then we've got nothing. A rise time and a fall and nothing. Then we've got a rise time and a fall, but because we've got a pixel right next to it, it doesn't get a chance to fall right the way back to 0. So consequently we rise again in the same time, and we can climb the power a little bit higher towards the target that we're aiming for, and then it falls and it doesn't drop down again as far, and eventually after, in this particular case I've drawn it 3 pixels, I've reached the maximum. So, and then we drop down, and with 2 pixels we get to a different level, and with 1 pixel we get to this level. So basically what I'm saying is if we've got 1 pixel we achieve this much burn. If we've got 3 pixels, we can achieve this much burn. And if we've got 2 pixels, we can achieve this much burn. Now that's a variable amount of burn depending on the grouping of the pixels. It's getting quite complicated, the way in which all these factors are interacting together. But the point I'm really making here is that this piece here is a constant. So the amount of time it takes for the beam to go up to a target value, it's aiming to get to 11%, remember, but it never got to 11% because we didn't give it enough time. It had to switch off. This is why I keep labouring the point about these times, milliseconds, because at 5 milliseconds, here's what the picture looks like. Now, if it was only 3 milliseconds, we would have even less time to go up and come down. And goodness me, look what happens at 0.85 milliseconds. We get hardly a chance to start before we've got to stop. So what I'm really saying is here, the response time of the beam itself to turning its power on and turning its power off to different levels can have quite a significant effect on the amount of burn that we get and the density of the burn that we get on these pictures. And remember earlier I was saying to you, I was trying to find an explanation why our dots were not all dark black. Well, here we are. We've got different groups of dots here which operate at different powers. Where we've got groups of 3, 4 and 5 dots up here, we've got a dark burn. But where we've only got single dots, we've got hardly any burn at all. And then we may have double dots and triple dots. That isn't what I was expecting, but that's what we're going to get if we drive the resolution too high and if we run the speed too high. Remember, the resolution is going to affect the time. But of course, this is at 50 millimeters a second. So if I increase that to 100 millimeters a second, I would have half as much time on each one of these. And if I ran it at 200 millimeters a second, I'd have a quarter as much time. So time is a most important factor because it's all related to the response capability of the power supply and the laser tube to produce a sharp dot. Now that was hard work and I hope you've understood that. It is the explanation that I'm putting forward for this strange pattern of variable burns. Now, we shall see in the next session, when I start doing some real pictures, how this effect, this strange effect, which I'm calling pseudo grayscale, because technically these should all be black, all the same density, but they're not the same density. So we've got degrees of grayness in here, but we're not using grayscale. This is what I call a pseudo grayscale system. Well, I'm going to leave you now where we started this session off. That there being a filled vector piece of text and that being a bitmap piece of text. Now, as I said to you, they don't look any different, but believe me, I think after this session you can understand that they are done in a completely different way. Now, this is a very simple exercise. In the next session we shall deal with real photographs, where I think you'll be quite surprised at some of the results we get.